So I'm going to be talking about work that I've been doing really over the last 10, 15 years, looking at the East Africa Rift with MT, and also drawing on work done by my colleagues, most notably Sinan Ozaydin, who's at University of Sydney, Paul Bedrosian at USGS, and Martin Musila at Toulouse. I've been at universities kind of all over the place when I've been doing this work. I'm now an adjunct at the University of Tasmania, but my actual job now is doing geophysical consultancy with Volks Geophysics, so I don't get as much chance to think about nice active tectonic problems anymore. So it's great to be here today to be able to talk about it. You were at a talk series on rifts, so I'm going to presume that people have at least some reasonable background with the East Africa Rift. That really, as we'll hear in the next talk, is kind of most developed in the Ethiopian Rift segment, where we've got kind of incipient oceanic lithosphere being formed, and then kind of barrels down towards the Tanzanian craton, where there kind of splits here into the western branch and the eastern branch. And as we'll see later, then keeps heading down towards Mozambique. I had my first opportunity to go to this part of the world in 2006, I believe. And we were in Tanzania, kind of on the craton, and we were looking at eclogites. Had nothing to do with the rift at all. And as I was kind of looking through that data that we collected and trying to figure out what story I could pull out of it, which it turned out there wasn't really any story I could pull out of it, and then learning more about that part of the world, realising that a much more interesting story to tell and to look at would be the rift itself. And what really interested me was, as I said, the rift really comes pretty directly down through Ethiopia, and then, at least at a map view, appears to kind of hit this rheologically strong region in the Tanzanian craton, and then split into the eastern branch and western branch. I actually thought that was a really intriguing kind of behaviour, and then sort of that it illustrates that it's a part of the world where we can maybe look at what's the contrast in the lithosphere between those regions, between the craton and the rift, that means that the rift is weaker and is rifting, and the craton is stronger and is not rifting. So at the time, I was doing a postdoc. I thought I could use kind of a really nice, clear, big picture result that would give me a beautiful image that would maybe get me a nice high-profile journal paper and get me a job somewhere. So I thought this would be a good place to go and do a nice MT transect. So went out there in 2011 to do this work. And I was really expecting to see a clear contrast between kind of the strong craton and the weaker rift. So this is kind of where I was doing that work. So we're here crossing from the Tanzanian craton onto the rift. And this part of the rift is what we would call the North Tanzania Divergence, where, as I say, we're kind of, the rift is bifurcated around the craton. We're in the eastern branch of the rift. And we have quite a lot of magmatism here. So Oldonyo Lengai, Kilimanjaro, some sort of quite famous volcanoes. And then the rift kind of peters out a little bit. So then south of that, there's some faulting. And then it kind of, as we keep heading south, it kind of peters out. So it's kind of considered this sort of divergence zone. And what I was expecting to see was that the craton would be quite electrically resistive in the lithosphere and the rift would be quite conductive. And I was expecting to see that for a couple of reasons. Firstly, the seismic images across that region, which show the craton as being quite seismically fast, which is what we might expect from a craton. It's colder, it's more depleted, and seismically fast. And then, as you can see here, much slower seismic wave speeds heading up the eastern branch because it's hotter, there's magma around, it's seismically slower. I thought that that would be likely to be what would reflect what we would see in the MT, especially that high temperature, that temperature contrast from the craton to the rift. And the other factor that I thought would control that is also the hydrogen content in the lithosphere. So these are some experimental results on the conductivity of olivine. This is sort of an old compilation, and different labs see slightly different things, but always basically the same story, where so the different coloured lines are at different temperatures. So as the olivine gets hotter, it becomes more conductive. Again, that's why I expected in the rift we would see higher conductivities. But also as the hydrogen content of that olivine increases, then it also becomes more conductive. So the hydrogen there is a point defect within the olivine. Olivine itself is an anhydrous mineral. And so but hydrogen will often sit in those minerals as a point defect. When it does, it diffuses really quickly and easily, and it enhances the conductivity of those minerals. But really importantly, hydrogen is also a strong control on the rheology of olivine and pyroxene and these kind of bulk mantle minerals that are nominally anhydrous. So the rift, which is weak, we might expect there to be a lot more hydrogen in those minerals, and that's part of why it's deforming. And then if there's a lot more hydrogen in those minerals, we would also expect them to be more conductive. So I went and did all this work, expecting to see a resistive craton, a conductive rift. And then this is the model of what I did see, which is exactly the opposite of that. So here we are in the craton, looking down to 200 kilometres depth, and the lithosphere beneath the craton is quite conductive, and contrasts with the lithosphere here of the rift, the Mozambique belt, which is quite resistive. We're looking at sort of 2 or 3 orders of magnitude contrast in resistivity from the more conductive craton to the more resistive rift. So this was a big surprise and took a lot more thinking to figure out what was going on than that simple model that I was expecting, as any good science does. And so I interpreted that the craton must be conductive because there had been some metasomatic events in its past that had introduced probably hydrogen and maybe some other conductive minerals in there. And this is something we actually see in cratons all around the world, where they tend to be relatively seismically homogeneously fast. In MT, they tend to be quite a lot more complex, and there are quite a lot of conductive zones signifying that there has been past metasomatism. And the rift, then in thinking about it more, I thought, this is actually a region that has seen a lot of tectonism. Prior to the current rifting, there was a lot of Pan-African deformation, and really kind of high-grade metamorphism and melting. Really, this is a region that has experienced a lot of melting in the past and is experiencing melting now. And really, actually, what we should expect as a result of that melting is that it's become dehydrated. Any of that previous hydrogen that was in there has been melted out. Any other hydrous minerals have been melted out. And maybe not a surprise that it is actually quite resistive. But a challenge then to understand then this rheological problem. And so then that forced me to think a lot more about the controls on rheology, putting different numbers into equations to see how we could explain the fact that if the rift is dehydrated, it can still be weaker. So certainly the higher temperature helps, but then other factors that we're not necessarily seeing with the MT could be controlling that as well, such as grain size. So again, in the Mozambique belt, we've had all of this relatively recent deformation. If that's decreased the grain size there, then that's going to make that region weaker, even if it is dehydrated. So that was back in, so here's my interpretation of that, the grain size is likely to be a strong control on the weakness of the rift. And then really any compositional or fabric or structural effect that then allows the melt to get in there, then once the melt gets in, then that's going to have a huge effect on weakening that region even further. So it was back in 2015 that we got that work out. things progressed a bit since then in our capability and the data. So while I was out there collecting that data, there was also a French group out of the University of Brest. So this was Pascal Taritz and Sophie Horto and Matthias Plasman. They were collecting more kind of focused data around some of the volcanoes. And so then we were able to then combine all of that together and then extend from those previous models that I ran, which were just 2D inversions, and then extend that into 3D inversions. This was Sinan Ozaydin, who had been my PhD student, is now a postdoc. He did this work when he was at Macquarie. He was leading this. And the results that we got from that, pretty similar. So the models are over on the right-hand side here. The MT models in this left column, again, showing a bit more complexity going on, but still in general, the higher resistivities beneath the rift and more conductive beneath the craton. But Sinan's also done a lot of work converting MT models into kind of compositional models. So these columns then on the right are looking at water content, so directly looking at that kind of hydrogen content from those MT models. And showing that then these dark colours, which are around where these volcanic centres are, in general, are also then highly dehydrated, going down into the lithospheric mantle. The increased data density enabled some more detailed work to be done, and then that within that broader picture that, yeah, as I say, the craton in general is more conductive and the rift in general is more resistive, that there is some more complexity there. And some of these conductive, they're still not terribly conductive, but not completely resistive channels heading up towards some of the volcanic centres. That could be regions where there is active magma in the lithosphere, just lowering the resistivity in some of those places. But in general, those higher resistivities really reflecting places where any of that metasomatic material that had been in the lithosphere has been melted out. And then another nice thing about this work is that there's been quite good geochemical analysis done on those volcanoes that's also shown that the early, especially the early stages of volcanism, were really where the metasomatic material from the lithospheric mantle was melted out. Just briefly in the last couple of minutes, that's kind of looking at the northern Tanzanian divergence. There's some other work as well. This was work, some data I helped collect when I was a postdoc at Lamont. This was part of a big project called Segment, which was the MT, but also passive seismic and active seismic and geochemistry and GNSS. So quite a lot going on in this project. Kind of enough going. There was a lot of field work, and unfortunately the postdoc was kind of long enough to do the field work, but not long enough to get all the models finalised and out. So this was work that, as I said, I did it at Lamont, so that was with Donna Shellington and Jim Gaiety and others, and then also with Paul Bedrosian, who's at USGS. So the last few years, Paul and I have been kind of trying to get these models finished and out, and now, thankfully, we have now Martin, who's working with Cindy Ebinger at Tulane, who's picked it up and is working on it again. So this is a much more densely spaced data set, so we can look more closely at some crustal features here. And as I say, now we're kind of in the very southernmost extension of the East Africa Rift. So we have the Rungwe volcano, which has is the most southernmost volcanism in the East Africa Rift. And then heading down to Lake Malawi Nyasa, which is non-volcanic, but just like quite an incredible, it's more than 500 kilometres long. The lake itself is 700 metres deep. And then the lake sediments are more than 5 kilometres thick. Just this really kind of incredible reflection of the rifting. Looking at the Livingston Fault and the huge elevation across that fault. And then, as I say, this huge drop beneath the lake as well. This is just a couple of recent models from Martin's. So we're looking here at 3 kilometre depth slice that, again, you might expect that what we would see here is a lot of high conductivity beneath the Rungwe volcanics. These are, relatively recently erupted volcanics. Far and away, the strongest feature that we see is the very high conductivity associated with the lake bottom sediments. And it's seeming, we're still doing analysis on this, but it's seeming like we can actually see more conductive and less conductive layers that correlate with regions of drier and wetter regions and times of higher and lower sedimentation. And then having the seismics as well is fantastic, because then we can also correlate these MT images with the seismics. Moving slightly deeper within the crust, really with this slide just trying to make the point that there's a lot going on here, and I guess with all of these rifting environments, that the pre-existing geology is such a big control on the rifting behaviour. And then it's also a big control on the geophysics as well, and understanding what it is that we're seeing in the geophysics. So this is part of the challenge here, especially as we go deeper, is pulling apart whether the features that we're seeing are actually related to the current rifting or to previous geology. But in this slide, I just wanted to really point out that here in the mid-crust, there is a lot of high conductivity spatially associated with those Rungwe volcanics, which probably is at least partly due to magma. And as we go down in the crust, then that extends much further away from those volcanic centres. I recognise I don't have any time left at all, so I'm just going to say that in terms of me and my own career, this work on the East Africa Rift, where that's just such a clear indication of kind of active geology, has been so instrumental then in thinking about other things. So that work really thinking about rheology and what it is that we can use from the geophysics to understand rheology really drove work that we've done in Greenland and in Antarctica, using geophysics to model mantle rheology for glacial isostatic adjustment models. And then understanding, especially mineral systems, where we might be looking at rocks that are billions of years old, but those exact same processes of metasomatism and melting, and then understanding actually what it is that we're expecting to see in the lithosphere, where we're expecting to see conductors and resistors associated with those things. So I'll stop there. Thank you very much.
Thank you so much, Kate. That was wonderful and nice to see moving beyond East African Rift to applying it other places. I have a quick question, and then maybe Derek has a quick question. How much has there been of joint inversion since you've got, particularly in the Lake Malawi area, you've got so many data sets?
Yeah, that's a good question. Not yet. So this work that Martin is doing is it's the first integration that we've tried to do between the MT and seismics. And the plan is not at the moment to do strictly a joint inversion, and more just kind of separate inversions and then constrained inversions from those results. But having said that, we have kind of high hopes for what he'll do between now and the end of his PhD. So yeah, we'll see.
Very cool, very cool. Derek, do you have a quick one?
Yeah, quick, thanks. Do you have any insights from your data as to why the southern end of the eastern rift penetrates into the craton? It sort of always puzzled me why the rift chooses to go into the craton and then stop. Why not keep going around it?
Yeah, I agree. That's also always puzzled me as well. And the short answer is no. But especially in this more recent modelling that Sinan has done, we do see a bit of low resistivity there where it is penetrating into the craton, whether that's because there's magma there and that's creating the low resistivity and it's a chicken and egg, I'm not sure. But yeah, short answer is that I wish I had a fantastic pithy response to that, but the short answer is no, I don't.
Thanks.